Now, let's consider the quality and explanatory power of the multiple regression model. As we have discussed in the context of simple regression, the coefficient of multiple determination quantifies the percentage of variation in the dependent variable explained by the variation in the set of independent variables. For instance, in our heating cost case study, we can employ the regression and the total sum of squares from the ANOVA table to compute the coefficient of determination, yielding the value of 0.804. This indicates that 80.4% of the variation in heating cost is accounted for by the three independent variables in our model. The residual 19.6% can be attributed to random error and variations stemming from independent variables not encompassed in our equation. However, the coefficient of determination often increases as more independent variables are added to the model. To mitigate the influence of the quantity of independent variables on the coefficients of multiple determination, we can employ an adjusted coefficient of determination. This matrix can decrease as the number of independent variables, denoted by k, rises. The adjusted R-squared equation is given by 1 minus MSE over MST equal to 1 minus SSE over n minus k plus 1 divided by SST over n minus 1, where n represents the number of observations and k signifies the number of independent variables. Adjusted R-squared provides a more conservative estimate of the goodness of fit of a regression model compared to R-squared, as it accounts for the number of independent variables in the model. While R-squared tends to increase with the addition of more independent variables, even if they aren't significantly related to the dependent variable, adjusted R-squared compensates for the number of independent variables in the model, penalizing the R-squared value for including non-significant independent variables. In conclusion, a high adjusted R-squared implies that the model accounts for a significant portion of the variation in the dependent variable. On the other hand, a low adjusted R-squared may suggest that the model may not provide an optimal fit for the data. In the heating cost case, by plugging the values from the ANOVA table into the equations described in the previous slides, we can obtain the adjusted R-squared as 0.767. This adjusted R-squared value is smaller than 0.804, the regular R-squared value. In practice, we should stop adding an independent variable into the model if the adjusted R-squared starts to decrease after adding that specific independent variable. In these slides, we demonstrate that the R-squared and adjusted R-squared can be computed based on the ANOVA table. Because the ANOVA table contains the information of SSE, SST, MSE, and MST, we can compute the corresponding values of the R-squared and adjusted R-squared, which can be found in the regression statistics table as well. We now talk about the standard error. The computation of the standard error in a multiple regression model is similar to that in a simple regression model. Standard error is an important concept in regression analysis, used to assess the precision and reliability of population parameter estimates. It measures the likely variation of the sample mean from the true population mean due to random sampling error. The value of the standard error is calculated as the square root of the mean square error. A smaller standard error indicates less variability in the sample mean, providing a more precise estimate of the population mean. Standard error is particularly useful when comparing the predictability of different multiple regression models applied to the same dataset. We can utilize the information provided in the ANOVA table to assess the standard error. The residual sum of squares, SSE, is obtained from the ANOVA table. The square root of the mean square error, MSE, which equals 2,606, shows that $51.05 is the typical error when using this equation to predict cost. A smaller standard error indicates a more accurate predictive equation.